say is that H is embedded in G, and so a balance cut in the sparse graph H. So this is the sparse graph. A balance cut in the sparse graph is a balance cut in the original graph. So the cut is almost the same as the cut in G. A cut in H is almost the same as a cut in G. I will prove all of these things and how do we find these sparse graphs H, which is a kind of simplification or summarization of a very complex graph G. And let me define that an alpha minimal cut is a cut whose weight is at most alpha times that of the global min cut. So C is the minimum cut value and V is the ST min cut value. And the result of Karger is that 1 plus epsilon minimal cut is in order of m plus n over epsilon 3 time, and if you use Monte Carlo, and it is of order of m over epsilon plus n over epsilon 3 time if you are using Las Vegas. And this tilde, in computer science, it is just a shorthand for saying that it is order of Gn log k of Gn. I mean, there exists k such that this is order of that. And so we, given an unweighted G, we construct a skeleton H. This is a skeleton. It's a random subgraph. And G is your original unweighted, possibly unweighted G. Possibly, I mean, we assume it is unweighted, but if it is weighted, no problem. We just, for example, if the weight of this is 2, we just say, okay, it's just 2. So it's not a big deal. So we can always go to the smaller scale. And so C hat is the minimum cut of G hat, and G hat is like expected value of G. So minimum expected value of any cut. And we want to show that as long as C hat is sufficiently large, every cut in the skeleton takes on its expected value. And I just finished this work of Karger, which is very historical and old, but very interesting for me, with his sampling theorem that says that let epsilon be square root of 2d to ln of n C hat, then with probability 1 minus order of 1 over nd. So this one becomes large with high probability. Every cut in skeleton of G has value between 1 plus epsilon, that expected value of C, and 1 minus epsilon. And that's enough for the work of Karger. I want to show you a bigger perspective, much more general, much more beautiful. And that's the work of people like Rohit Kandekar, Umesh Vazirani, Satish Rao, Harold Raki, we should pronounce it Raki, Sanjeev Arora, my favorite. So many interesting and very genius guys. So let's write their names and their articles. So in 2008, we have optimal hierarchical decomposition for congestion minimization in networks. This is the work of Harold Reiki. And in 2009, we have a very interesting article by Rohit Kandekar, by Satish Rao. This guy has written many articles in metric embedding as well. That's why I like him. Umesh Vazirani. Oh, there is another Vazirani. He's Vijay Vazirani. He's the author of the book Approximation Algorithm. It is interesting that both of these Vazirani guys are very genius. Both of them are very good. Both of them are Indians. And so this is the work in 2009. The article is Graph Partitioning. And this article is cited by several people, maybe more than 500 articles. Graph partitioning using single commodity flows. And that's why I only explain these unique articles. I don't explain any article. I just pick very unique articles like this. Shows that Sparse cut can be approximated in log 2n factor in O tilde n plus n to the 3 time. So using polylogarithmic single commodity max flow. So just iteratively employ max flow to embed an expander flow, to thus providing a certificate of expansion. So I will explain what I mean by iteratively employ max flow. We probably use some game which is called cut matching game. So the Sparse Cut Problem is very interesting. It's a kind of graph partitioning. And as you know, in graph partitioning, there are three approaches. The first approach, spectral methods. But unfortunately, it is only good for high expansion. It's very dense and very high expansion. But there is another approach which is use linear programming for this is my favorite, for multi-commodity flow. For several reasons, this is my favorite. And the third approach is metric. I love metric embedding as well. Metric embedding by people like, there are several people, but I just write Rabbani, which is my favorite. Yuval Rabbani. And as I said, most of the genius peoples in metric embedding, field of metric embedding, are from Israel. And some of them are from France, and some of them are from Germany, but most of them are from Israel. And so there are three approaches for graph partitioning, and I love this one. And in my future article, I combine these two. And so the relation between expansion and minimum congestion is the work of Sanjeev Arora. And the expansion of graph can be closely approximated by finding an expander that can be embedded in G with minimum congestion. So the difficulty is identifying vertices on each side of the cut to find a sparse cut using max flow. And the idea is that we iteratively construct expander H of low degree. So it is a low degree. So we embed it in G, as I said in the work of Karger. So the idea is iteratively construct an expander H that can be embedded in G with a small congestion. And I will explain what is cut matching game. It's a two-person game to construct H. So to construct this interesting H, we use cut matching game, which is very beautiful and very practical in practice as well. So we start with n isolated vertices, and then in each iteration the cut player says I want to bisection of vertices, and the match player says that I want to delay it, so I pairs up vertices across the bisection into a perfect matching. So the cut player just wants to bisect and the match player just wants to match. For example, we have this one. We divide it, we cut it, and after that the match player wants to match it. So in this article there are two subroutines. There are just two subroutines. First one is find bisection algorithm, and then it goes to flow match. And then, so it's a game, each time one of them works, and finally, after many steps, it converges. But it doesn't take too much. I mean, so in the third step, the cut player wishes to minimize the number of rounds before the union of matchings, and has constant edge expansion. So we can have a matching player using single commodity flow. This step is done using single commodity flow. I mean, one commodity from I to J like this is enough, so that in the original graph G is like this, and in the embedded graph is just one edge. And we try to approximate that. We want to prove it in several articles and research papers that the cut is almost the same. We can approximate it. So that's why the interesting connection between the cut and a flow in a multi-commodity flow produces some infrastructure for future articles, because it's very interesting, and you can somehow encode your knowledge, encode the knowledge of your algorithms. And so let's start by the Sparse Cut Problem. As you know, the expansion of cut S and S bar is called phi of S. It is the number of edges between S and its complement divided by minimum of the cardinality of S and the cardinality of S complement. So Sparse Cut problem is to find a cut with minimum expansion. So phi of G, we want to minimize phi of S over all possible SNS bar. So if F is in H, F is an edge in H, and it corresponds to a flow path in G. For example, we have a path going from I to J in G, and in H, going from I to J is just one edge. G is unweighted, but H is weighted. And so we route a demand D. I will explain it in next article, but not this article. So we call a graph expander if expansion is at least half. And we say that H can be embedded in G with congestion C if a flow of C of F units can be routed in G. So this is a flow, for example, from this is G, and this is H, which is H is embedded in G. And the G graph, we can say that H can be embedded or routed in G with congestion C if a flow of CF units can be routed in. So going from I to J in the embedded graph, I mean H is embedded in G. From I to J it's just an edge E, but it is separated in different paths going from I to J. So we have a flow of CF units. For example, let's say CF divided by 3, CF divided by 3, CF divided 3. If you sum all of them, it becomes CF. So CF flow goes there, and then it's just we represent that with just one edge, and with a weight of CF. So we represent it by that, without violating the edge capacities. And we do not violate the edge capacities, WE, by a factor more than that C. And the observation is that if an expander can be embedded in G with congestion C, then every cut in G has expansion at least order of 1 over C. And thus such an embedding can be thought of as a certificate of a lower bound on the expansion G. So let's just write the theorem that says there exists a randomized algorithm. Of course, I believe that P is not NP. I'm that guy. So there exists a randomized algorithm